afternoon, everybody. Thank you for joining us, and just apologies for the little delay there. I'm Christine Thompson. I am the General Manager of IAPA. Today we're going to be sharing with you the results of a collaborative research program test that is conducted out of QUT in partnership with SIAM, Queensland Government and Transport Main Roads. The findings from this study demonstrate the far-reaching uses that these models can have in our industry, and in particular those that are working in the area of risk management. For this webinar, we'd ask you to get involved and to be interactive. We will be taking questions during the presentation. There is an intro box down on the far left where you can type in your questions, and where we can, I'll integrate those within the presentation and address them to Daniel so that he can respond to you. After today's session, we will format a copy of the webinar for you, and we'll be sending out a copy of that via email, and we'll also be publishing it on the IAPA website so that you can either share it with friends or you can download it yourself and review. So that will be a copy of the webinar and a copy of the presentation. Okay, so without further ado, I would like to welcome you to today's session and now introduce Daniel. Daniel Emerson is a PhD candidate at QUT University, and he is also part of the team that's conducting this research program. Daniel has 35 years of teaching experience and is also a enterprise mining teacher at SAS Enterprise Miner. He's quite an impressive history, and Daniel, I'd really like to thank you for being here today and for taking the time to prepare this presentation for the IAPA membership and for taking the time to run through and do this. So I'll now hand over to you, Daniel, and let you run through your presentation and answer questions as they come up, and over to you.
Thanks, Christine, and I'd really like to thank Richard Green for all the work that he put in helping us get this presentation going in Queensland a little bit earlier, and it's really terrific to be able to share this a little bit wider. Okay, this has been a team effort, and there's myself, there's Daniel, and Professor Richi Nayak, who's worked in data mining over many domains and with over 150 papers and 800 odd citations. From the road management side, we have a practicing engineer, Justin Weligamage, who also has taken a real interest in road research, and and this shows in the number of papers that he's produced as well. As Christine said, it's actually a collaborative effort organised by SIAM that was funded by the Commonwealth Government and involved the Queensland Government Main Roads and QUT, which is where we came in. Okay, so we're looking at analysis in complex data, and the current situation, we find that manually managed models are formed on homogeneous data where we have a single class of data to produce models. And the main drawbacks of this is, of course, that it's fragmented, it's enterprise resource hungry to maintain all of these models, and it's limited in direct decision support. Our proposed solution is to produce an enterprise-wide machine learning methodology that's rapid over a number of hours. It can run through the full data set of the enterprise, and it has direct application in decision support. So individual roads or whatever your domain can be placed in and classified and analysed for risk. The future directions look at the refinement and wider deployment of the methodology. Okay, there are a number of themes that have permeated through the research, and I just want to highlight these before we start. So it's descriptive versus prescriptive analytics, modelling on homogeneous as opposed to heterogeneous data, first principles modelling versus empirical modelling, the knowledge environment and the need to make it dynamic so that you can have a real understanding of the data before you model, the role of the human as opposed to machine learning, and in fact getting humans doing high value activities rather than trying to copy the things that machines actually do better. And finally, the information lift from the road crash data has been absolutely terrific, and it's sustained the project for as long as it's actually run. Okay, so if we have a look at the problem, generally at any organisation, we have to make decisions about allocating scarce resources, e.g. those sorts of things like money, equipment, people, time. And the key thing here is usually it's in the face of uncertainty. And we're all used to making decisions in that state. In road asset management, it's the same thing of scarce financial resources across the whole road network to meet the stated goals of that network, particularly road safety. And there's a balance of getting the best out of the money. In our analytical landscape, we have descriptive analytics which actually define the problem. And we have this really rich heritage of from DBMS and business intelligent technologies of OLAP, machine learning, visualization, which Hass actually points out is absolutely fabulous in defining the problem. However, the movement of our research is to go into prescriptive analytics that actually gives us solutions to the problems. And at the moment, from Hass's paper, there's the expert systems, which are human devised models, and we're actually looking at moving into empirical machine learning deployments, replacing or working with expert systems to overcome some of the problems that they face. I just want to share one of our studies that actually illustrates this difference quite dramatically. So we actually have resolved road types into their various classes and examined the crash type probability, e.g. the types of crashes that a given road may have. If we look at the axis on the left, we can see that we actually have a number of clusters which go from cluster 0 through to 13. And on the right-hand side, we actually have the crash types, and we've highlighted a few here, including head-on, hit pedestrian, hit parked vehicle, overturned. And these bars actually show us the relative importance of each of those crash types. I want to focus on cluster 13, and in particular looked at the overturned, which is one of the key types that make this a particularly dangerous road. And we can see here that cluster 13 actually has quite a high overturned count in comparison to the other road types. But when we look along the various crash types, we can see that a profile is actually defined by these bars, and from road type to road type, the profiles are different. And so for each road type, we can actually develop this profile, which actually tells us what the problem is. So we know that on this particular type of road, we're likely to come across these crash types like overturned, fixed hit obstruction, head-on down this end, and so on. If we plot all of the crashes across by geometric coordinates, we'll find it actually defines the road systems, the main road systems in Queensland. And here we have Brisbane down here, we have Gladstone, Mackay, Townsville. And if we zoom in on a section of that, we can see the clustering that was actually done by the expectation maximisation methodology, my absolute favourite, really fits the domain expectations. we can see in the towns we've got these red and purple and blue clusters, so in Townsville and Mackay. In these small towns we've got the red clusters, and connecting the towns we actually have the main roads that are made primarily of this road type 13. And so that when we can identify as we move along a road type the types of problems that we're likely to associate, or the types of crashes that we're likely to have on these roads. And so we can see here the arrows actually point out roads with those particular types. Now we're hoping that in the future we'll be able to take this information through your smart device and actually tell you what the problem is. So in other words, when you come onto a given road, your device will actually report that the crash risk on this road types are going to be, which defines the problem. On the other hand, prescriptive analytics, we would want the data centre to be analysing your particular location, your speed, and your position on the road, and actually tell you to actually lessen your elevated crash risk. You would need to reduce your speed, change lanes, drop back, and so on. And so this actually models a solution to reduce risk. So the prescriptive analytic research is about assessing the consequences of alternative design, e.g. roadway design, investment or policy choices, and also, in our case, the operational parameters of the service that's actually being delivered as you travel along the road. Okay, if we look at the way that decision making is currently made on roads, and we're not trying to supersede this but actually support it, it's based on the judgment of the road engineer following best practice and constrained by the actual road crash rate. So therefore if the road is dangerous, we need to apply more of the particular design parameter. And this is from the manual of the Queensland Department Transport Main Roads from 1913. Looking at the diagram, we have here the benefit or the cost benefit, and here we have the proportion of the parameter that's actually applied. In this particular case, we're interested in road surface friction, and so we can actually apply a range from a lower bound to an upper bound, and the better the road surface friction, the lower the crash rate or the greater the benefit. However, we find that there's a reducing cost benefit. And this actually shows us the skid resistance heuristic. So we can see here we have a number of roadways which progressively become more risky, and as they do, we actually find that the skid resistance, as you would expect, actually increases. And this is used worldwide. And however, a need for a data-based risk-based decision support was recognised in this SIAM skid resistance project, and so this is how we became involved. And the risk-based method that will actually will discover the factors allowing optimisation and design of the operational factors to reduce risk.
Just going to take this opportunity to pop in and say hi, and just to see that if anyone does have any questions, feel free to type them into the box.
Okay.
Thanks, Daniel.
So let's have a look now at the enterprise-wide modelling environment. So up until now, heuristics have played a very significant role in dealing with complexity. We find a solution, a fairly simple solution that's trusted, that's tested, probably tested in the courts, and decision makers are very comfortable with them. And in fact, the Occam's razor of keep it simple, stupid, works very well. However, when we find ourselves modelling, we actually can see that there are two main types. We've got this deterministic modelling where we have experts trying to make models to represent the underlying processes, and Saltelli points out that this works quite well when we have scientific phenomena that we can understand. On the other hand, as the dimensional size of the data increases, it becomes more difficult for the human to understand, and so we rely on these empirically based methods such as the regression models, and so on. However, and these are generally done on homogeneous data, so we have a single class of data where we produce a model that actually generally contributes to understanding of the heuristics. But we end up with a whole heap of different models that are very loosely related and can't be directly applied. So our goal here is to use multi-class machine learning that can actually recognise and analyse all of the data and all of the classes and describe them so that we can have a single model, single integrated model. And in our methodology, we've managed to bypass the missing values that are so prevalent and tends to fragment the data. And we, in this methodology, there's a data-wide navigation index, so that when we're trying to place an instance into the network, it can be done on its characteristics. And so we come up with model rule extrapolation, which is this integrated enterprise-wide modelling tool, which works with heterogeneous data. And so in our icon here, we show that all of the pieces of the jigsaw are highly integrated. Now, Haas with prescriptive analytics talks about taking all of these pieces and putting them together in a network of knowledge that leads us to an outcome. And we feel that our methodology will actually provide an enabling technology for this methodology, as well as being standalone. Okay, so traditional roadway research has tended to focus on the aggregate traditional data modelling from roadway segments, where we generalise crash and come up with rules, and which set our heuristics and set our goals. And so they support our strategy documents. In an exciting move, we now have real-time data collection which actually identifies where the crash is likely to occur, and these can be used for moderating road speed, as seen by signs like this that actually change in response to the traffic. Our goal is actually to modify the traditional approach to provide a system-wide assessment for design and operational decision support. The current-based system, the Australian National Risk Assessment Model, it actually is made up of 30 generalised independent models, and that's available through these particular sources. However, they describe that there is some difficulty in matching the roadway to the model, and it results in model inaccuracy. So our question is, given an integrated approach, and with any modelling there's this inherent uncertainty, well written by Saltelli, and will an integrated approach provide a sort of a more accurate and exceed the utility and economy of having a number of human devised models that need to be manually matched to roads? Okay, so what's model rule extrapolation all about? Well, it's about applying a model. Sorry, start that again. The actual inspiration for doing this actually came from the fact that we were making models and prediction gave no value to risk abatement strategies. What we were really looking for was the effect of changing a variable, and so this naturally led us to an extrapolation-based scenario. Now, extrapolation has been used widely in analytics. However, how this is different is that there are a number of models involved, and so as a given variable like the skid resistance changes, it actually invokes or instantiates different models on the way through and is able to represent a non-linear curve. It looks a bit like Mars. However, it actually allows analysis of heterogeneous data, and it produces multiple curves from the data, actually one for each instance in the enterprise. Okay, so what are our objectives? Well, we want to actually provide a decision support tool that's trained on the enterprise-wide data. We want to produce individual risk curves to automatically assess each instance. So from the whole network, identify roads that are actually likely to be risky and provide simulative what-if capability to optimise each instance. Okay, we want to actually be able to judge on latent risk rather than an express risk as is done now. Utilise the huge volumes of observational data that are generally viewed as homogeneous. We want to unify that into a single huge data set that will inform our models. We want to overcome missing values, and also the controlled experiment itself is problematic in the effect that it actually isolates variables when we're trying to find the effect of the independent variable on the dependent variable. And this actually exacerbates the lack of understanding among variables as described by Carney in his 2008 skid resistance study. Okay, so what algorithms can we use? And in fact, the really good thing about this method is that we can use an off-the-shelf algorithm. So we want one that predicts numerical data. We want the output to be in rules rather than individual point predictions like many tree methods do. We want to manage data that originates from diverse stochastically generated processes. In other words, we've got a whole heap of different classes of roadway here, which the variables from them interact differently from class to class, and this is not well represented by a single rule or even a single tree. So we have a table which summarises some of the models that we tried, and if we look along the top, we can see we have a single expression column, we have a single structure column, and a multiple structure column. Looking down, we have a calculated value so that when you ask for an answer, it comes up with an average value, as opposed to an expression which is a single linear expression involving each of the variables. So, linear regression or support vector machines just did not perform because they're confused by the multiple classes that they're trying to analyse. When we go to a single structured tree, we find that they work quite well, and in fact the CART methodology, classification and regression trees by Bryman, 1984, and a part of the currently available, and RepTree, a Weka implementation, worked very well. We were very surprised that neural networks did not, but we felt that the fact that the different classes actually confused the processes, and even though they work exceedingly well in single class but complex instances, situations rather, they don't or do not appear to work well in multi-class situations. And in fact, just showing how well they do work, there's a reference here that you may like to follow up on. We found the model tree, which actually, instead of providing just an average like card or rep tree, actually provides a rule at each leaf node, worked well as well. However, when we go to multiple structures, we found that random forests performed much in keeping with cart and rep tree. However, M5 rules provided the solution that we were looking for. These work well by actually having random forest, for example, supports a number of trees so that when a particular class is being classified, it finds the correct tree for that class. And M5 rules works in a similar fashion. When we look at the results, we can see that M5 rules has been selected. It's got actually produced correlation coefficient of 0.93, which means that it accurately classifies about 90% of the instances. With a minimum predicted value of 1, it actually produces 0.86, which is fairly close to that value, and the maximum of 100 is predicted at 98. Now, the really good thing about M5 rules is that it has a small number of rules to do this. When we look at, say, M5P, which is a single tree, it actually generates 1,100 rules. And we believe the reason behind that is that a given relationship is actually fragmented to allow the split of a major class, and it actually shows up in further splits further down in the tree. And when we look at neural networks, we find that the predictive value is quite low at 0.71, accurately predicting only about 50% in a similar way to linear regression or support vector machines, and also had quite large outliers. And so we've actually decided on M5 rules as our off-the-shelf solution for modelling. If we have a look at how it works, and I think I need some water at this stage. We take all instances, we then build a tree on the instances. The best rule is selected and placed over into the rules set. The instances that are covered are actually dumped, so they're taken out of the mix. The instances not covered are converted into temp instances, and the temp instances are used to build a new tree. And this is repeated until no instances remain. And so we end up with semi-independent rules which are better able to describe the multiple classes. The particular rules look like the following. We have a number of rules here going from rule 1 down to rule n. They have a precedent which actually describes the conditions to instantiate that rule, and there's a consequent which actually makes the calculations. And if we look here, we can see that in the precedent we have a number of conditions involving the lane count, the crash speed, the friction, and the traffic rate, and then we actually calculate the average using the seal type, the seal age, and so on, and including skid resistance here, which is our particular variable of interest. When we plot the actual versus predicted, we can see that we get quite a tight line, and in fact it is actually better than as shown in this, as shown where we have a series of box plots instead of lines here, that the predictions are quite close to the line. So we see an R-squared value here of 0.9, indicating around about 90% of instances are actually predicted accurately. Okay, so let's have a look at how the method actually works. Okay, so what we want is a model of linear rules from the heterogeneous data. We want to generate a risk curve by model deployment across an extrapolated range of the variable of interest, e.g. in this case skid resistance. We want to avoid the missing values, and this actually becomes a non-requirement because we have this extrapolation going on where we don't actually need to know the observed value of the skid resistance for this to work, and that's really amazing. And then finally, we want to be able to optimise the variable of interest on the risk curve and model changes to all risk factors and not just the skid resistance. Okay, so how does it work? Well, we take all crash data. We then sample the data that has a skid resistance value. So where we have complete records, they become our training data. And so we train the model. We then devised a set of a test range of skid resistance going from 0.15 through to 0.65. We then replicate each instance. So this instance here is replicated by the number of test range values, and so we end up with 11 copies of that replicate, each with a different value of the variable of interest. We then apply the model so that a prediction is made on the basis of each of these values up here. And interestingly, getting back to the controlled experiment, this emulates a controlled experiment because all other variables are kept constant and only the variable of interest or the independent variable is actually changed. We then optimise the crash rate, which say maybe up here, and we can actually place it further down on the curve and come up with a new skid resistance, and then further carry out simulations to optimise all variables. Okay, and we can see here we have the array of skid resistance values going from 0.15 through to 0.65, and as the predictions are made, the rules change. So in these first two here, rule 1 is instantiated. However, as the skid resistance changes, it calls in a different rule, and we can see rule 3 and rule 4 making the final 5 predictions. And we see a curve that looks, it's sigmoid, it's monotonically decreasing, and where we have a region of high risk and a region of low risk. We can then, in a case where we don't actually know the skid resistance, we can intersect the crash rate with the curve, and it'll tell us approximately what the skid resistance would have been. But that's of absolutely no interest to us. However, when we place our new optimal value further down the curve, it will actually give us a revised skid resistance value that will supposedly, hopefully, reduce the crash rate. So this actually gives us a tool that the engineer can use in their decision making. And this value will actually fluctuate through here, same way as your cup of coffee. If as you walk, it wriggles, and if the cup is too full, you have a spill, and the roads are the same. If this is placed too close to the threshold, the rate of crashes will go up. The skid resistance application of materials to increase the skid resistance will cost, and it reduces the risk. However, if we don't do that and the skid resistance is lower, the risk increases. So that they've got this ability to maximise according to the engineering requirements of that particular road. And interestingly, we really want to get the road down below the residual crash level, and we can see this one actually terminates somewhat above that. And so by changing those, what have been the control variables in the past, we can redraw that curve, or attempt to redraw that curve to bring it down into that residual risk level. These are some curves that actually were produced by the whole data set, and they tend to follow that reducing monotonic trend, with the exception of a few, which we believe is due to the low skid resistance on very low volume roads, but we need to test that hypothesis. Okay, so the application, we can see there's some examples here. What was a 3 was predicted as 0.28. What was a 12 was predicted as 0.86. What was 100 is 91.1. So they're relatively close. And these are some risk curves, and we can see one particular risk curve here. The actual crash rate is right on the curve, and with the application of the correct material, we can reduce the skid resistance and reduce the crash rate substantially. And it becomes very close to this line of residual risk here. In this particular road here, it's beginning to approach a high risk state. Skid resistance actually over time will reduce as the road is worn, and particularly in patches of acceleration like corners, off-ramps and so on, where the driver will actually need the roads for wear. And so this is what we mean by the not having to wait until the road actually starts to exhibit a high risk behaviour. We can actually assess the latent risk. And this is a similar curve showing similar characteristics to the prior one. Okay, now further, we have this simulation capability where we can change things like, for example, we can place an emergency stop lane in and actually see the effect of that on the curve. We can apply a number of effects in this particular one. Really not a good example, because for an actual crash of 28, it's predicting 15. But by having skid resistance only, the 15 reduces to 11.6, and by changing the carriageway type from single to dual, the crash count actually reduces further to 6. Okay, so the benefits are we have a single model managed for the enterprise-wide data. So rather than having to maintain a whole stack of models manually, we can do this in a single swoop across the data as data is updated. We have rapid machine learn rules from complex heterogeneous data, and this is actually beyond the human capability. And the profile provides an environment of the controlled experiment. It's prescriptive, allowing modelling of risk factors, and missing values are managed, and they no longer block this ability to perform enterprise-wide analysis. Okay, so in the new work, we're really interested in the uncertainty analysis. So Tully actually points out that it's a precondition of model goodness, and we need to be able to show the engineer where the points come from that actually draw the curve. Further, once we actually have our uncertainty analysis in place, when we make modifications or improvements to the system, we'll be able to judge their goodness by how closely these points actually follow the curve. Further, work includes model development, and we need to understand better the mechanism of empty extrapolation. Multidimensional data has huge volumes of empty space where there are no data points, and at this stage, our models will actually make predictions where none exist, and so we have plans to change the rule types to specifically state the ranges of the data. Further, we need to assess and develop the domain utility, including the enterprise-wide cost modelling, so that the best decisions can be made. We want to accommodate streaming data and actually functionalise the method so we can place it in process flows to make decisions, and then trial it in other domains, like, for example, in education, in fine-tuning the learning experience for children, in insurance, banking. We even feel that there's a place in the intensive care unit where we have a fast-acting situation involving many variables where this could actually provide information to help deal with crises. Okay, I'd just like to acknowledge the role that SIAM played in drawing the university and main roads together, as they do across the planet. They have they work in China, across Europe, South America, the US, and in setting up such projects. And we recognise the support from the Department of Transport Queensland that provided the data, and also the people to help us develop and assess this particular project. Recognise Dr. Rune Rasmussen and for the advice he gave. The modelling was performed with the algorithms from Weka, SAS Enterprise Miner and Salford Systems.
Thank you, Daniel. We haven't had any questions typed in today, but I think that you've probably raised quite a few, certainly when you start to look at how the application of these models can be used across different industries. And I'd really like to see the outcome of this for you, for it to be taken and considered against those other domain industries. So I think that it is really exciting. Socially, I mean, the research that you're doing is really coming up to help us in a social way really develop decision making and risk management in such a fast-paced world. So Daniel, I really want to thank you for your time and for sharing the research that you've been doing, and just for everyone who's been on the call today, please do feel free to type in and ask any questions in the survey before you leave. But also you can certainly contact us online, and if you've got any future questions that you'd like to provide for Daniel off the back of this webinar, we can certainly facilitate that as well. From the team at IAPA, we really thank you. We will be starting to run more of these webinars for you, because we really see the value in having people share the work that they've been doing and the application that they can be used across and reuse across different industries. So please do connect with us. We'll also let you know what events we've got coming up and educational opportunities as well.